Thank you for taking a look at this talk. My name is Anna Kornfeld Simpson, and I'm a PhD student at the University of Washington. Together with my three co-authors, we'd like to get you thinking about securing data center storage systems built on top of remote direct memory access, or RDMA. RDMA offers high performance, a few microseconds of latency, throughputs of hundreds of thousands or millions of bytes per second. This has led to deployment at large cloud providers such as Microsoft Azure and Alibaba Cloud, and significant excitement from systems researchers who over the past few years have published papers with a number of different types of systems built on top of RDMA. One of the ways that RDMA achieves this performance is by a technique called CPU bypass. Bypassing the CPU is a useful performance improvement because CPUs have become a bottleneck for packet processing. Network speeds have increased so much that the network speeds are now faster than the CPU. By removing this bottleneck, RDMA can make use of the faster network speeds. In order to bypass the CPU and, as the name says, directly access memory, the storage server has to perform some setup. The diagram on this slide shows an RDMA over Converged Ethernet, or ROCE v2 packet, including some details from the client that have to be provided by the server. First, the server must register a virtual address corresponding to a region of its memory that it wants to make remotely accessible. This registration process produces a pseudo-random capability known as an R key. After the server sets up connections, or queue pairs in the RDMA world, with the storage clients, it then has to convey this virtual memory address and R key to any storage clients that should have access to that region of memory. Then, on the data path, clients can use that remote memory address and R key to bypass the storage server's CPU. Let's look at an example. This example is from the Pilaf system, which is the earliest published storage system that we studied in our analysis in this paper. Pilaf's put operation does not use CPU bypass. It looks somewhat like a traditional RPC. The storage client sends its request off to the server's network card forwards it straight up to the server's CPU, and the CPU takes care of storing the data in its memory, and then explicitly sending a response back to the client via the NIC. The GET operation, however, looks a bit different. It is CPU bypassing. So the RDMA read operation coming from the storage client in this case contains that virtual memory address and R key. The NIC validates that address against the previously registered information, and then goes directly to memory to read the requested data and reply to the client. The CPU is not involved at all in this operation. Indeed, it has no idea that this occurred. RDMA comes from the high-performance computing community and was not designed with a data center threat model in mind. Over the past 2 decades, researchers have discovered a number of aspects of RDMA's security that need additional attention. In section 2 of our paper, we review these discoveries and provide citations. For a very quick summary here, there are issues with confidentiality as packets are in plain text. There are no packet integrity checks. Researchers have discovered denial of service attacks, including the flavorfully named PFC pause frame storms. See the paper for more. And just last year at HotCloud, Tsai and Zhang noticed that recent RDMA networking hardware was issuing very non-random looking R keys, which are supposed to serve as pseudo-random capabilities. So these are some security fundamentals that need further attention. But what about after that? We analyzed recent distributed storage systems that use RDMA published in the systems literature. The list of systems we analyzed can be seen at the bottom of this slide. We discovered that even after the security fundamentals from the previous slide are addressed, there are additional systems research and design challenges that we as a community need to be working on in parallel. If we want to provide security at least as good as pre-RDMA data center storage systems for RDMA-based systems, we have some additional work to do. Our threat model for this analysis is that of a compromised storage client. There are a variety of ways that this could happen in a data center environment. For example, if the application making use of the storage service is user-facing, then the storage client likely shares a virtual machine with a front-end web server, a piece of software that's proven difficult to secure. But however the adversary gets in, if they have root permissions and the ability to change a flag on the network interface corresponding to the client's RDMA NIC, then the adversary can read the RDMA traffic that goes to and from the client, containing memory addresses, R keys, and other necessary information to be able to then spoof its own RDMA reads and writes. I'll note that VLANs and virtualization do not help against this threat model of a compromised client. The adversary only needs to see its own network traffic from its own VM, if it's in one, to get all the information it needs to perform whatever bad it wants to do. As I mentioned, we identified a number of challenges. You can find them in detail in section 3 of the paper. We also have there a table of the systems we analyzed, the RDMA operations used by those systems, and based on our reads of the papers, what challenges each system uncovers. I'm going to highlight some of the challenges here, but I encourage you to take a look at the paper for more details. The first challenge is one that I am particularly concerned about, and it makes use of the CPU bypassing read that we saw in the GET operation for Pilaf. It also appears in, for example, farm. What if the CPU bypassing read is actually done by an adversary who has compromised a client and is trying to exfiltrate or steal data from the storage service? One of the first things that incident responders want to know after discovering and ending the compromise is what data was exfiltrated. In a traditional system, they might go take a look at the server logs and audit them for suspicious requests from the compromised client in order to figure out the period of the compromise and what data was accessed. Unfortunately, with CPU bypassing RDMA, there are no server-side logs to audit. Indeed, the server's CPU has no idea what data might have been accessed. This lack of auditability is a problem in the case of compromise, but it's also a problem in the general case, particularly if the data being stored is end-user data. Auditability is important. So, as researchers, we have a challenge. How do we preserve auditability while also benefiting from the high throughput and low latency of CPU bypassing RDMA? Another challenge also comes from removing the CPU from the loop. And that is that the storage logic, such as handling things like locking and unlocking values for reads and writes, now has to run on the untrusted client. This makes it hard for application developers to reason about the correctness, reliability, and security of their systems. The example on the slide here is a put operation in Dr. TM. It contains two different CPU bypassing operations. One to check and set the appropriate read or write lock for the data, and then the second to execute the read or write. If an adversary compromises a client in the system, it has no reason to follow this protocol of using the locks correctly. Indeed, it could unlock locks that other clients think they have, or otherwise muck with the correctness guarantees that the application developers thought that they were getting from RDMA. So as researchers, we need to think about what abstractions and guarantees we can offer applications so that they can reason correctly about their systems. A third challenge is particularly pertinent when storing end-user data, and that is providing some kind of isolation between different users' data so that it is more difficult for an attacker to exfiltrate all of it. Unfortunately, the performance characteristics of RDMA NICs disincentivize this. In fact, the caches of RDMA NICs need to hold both all the memory registrations and all the queue pair information for the connections between the server and the client. Since overflowing the cache would be really bad for performance, this incentivizes as few memory registrations, and therefore as large memory registrations, as possible. This makes it easier for the attacker to read the information it needs to access a whole bunch of data at once. The vendor's suggested solution here, called protection domains, unfortunately suffers from the same performance incentives for storage systems as the problem. With protection domains, the protection domain of the registered memory and the queue pair accessing that memory must match. Since in storage systems, we likely have multiple storage clients who all want to access the same region of memory, likely multiple registrations would be needed in order to have different queue pairs, but different protection domains, but have them all match. This does not work out well for the performance. And so, again, research is needed here. How can we provide notions of isolation, even better, permissions and access control for user data in storage systems built on top of CPU bypassing RDMA? So these are some ingredients for more secure CPU bypass systems. The ones I just mentioned are on the right side of this slide. There's a little bit more in the paper. Going back to the security fundamentals, I have hope that in the next few years, future generations of RDMA NICs will be able to provide things like high throughput cryptography on the data path with their more powerful processing. Combining this with the already existing centralized configuration management in the data center, things like Zookeeper, to distribute keys, that will be a significant progress towards addressing these security fundamentals. But if we don't address these system design challenges at the same time, we don't end up with secure CPU bypass RDMA storage systems. So, as you can see, there are a lot of big open questions for future research and a number of different flavors of questions. I look forward to seeing ideas and solutions for all the challenges we identified. And I wanted to leave you with some questions of my own. For those of you who are systems designers, what is your wish list for features to help support application security for applications built on top of your systems that use CPU bypassing RDMA? Does that wish list change if the applications are user-facing or not? And for all of us as researchers, once we get these better features and solutions to the challenges we identified, how do we get them baked in to RDMA and storage systems by default so that all applications can benefit from the increased security? If you have questions, feel free to email me at the address on the bottom of the slide or post in the HotCloud Slack or discuss during the live Q&A at the workshop. Thank you so much for watching.